So I think we'll start. It's already 9:38. Okay. So are you able to see my screen, all of you?
Yes, sir.
Yes, sir.
Yeah, fine. We'll proceed for today. So this is the last class we discussed, like what is meant by polarization and what are the different applications of polarized light and how to produce the polarized by absorption, reflection, refraction, and scattering events. Okay. So today we are going to see a phenomena of double refraction, as well as how we are going to get a double refraction phenomena in calcite crystal. Then we are going to modify slightly our calcite crystal to fabricate Nicols prism. Then once you know about the double refraction calcite crystal, we are going to define what is meant by positive crystal and negative crystal. Then we are going to see quarter wave plane, half wave. This is the content for today's lecture. Probably we can discuss these two parts maybe in the next class probably. Okay, we'll start with a double refraction. So many of you must have seen these images in day-to-day life. Have you seen this kind of images, especially this?
Yes, sir.
Yes, sir.
So why it is bent away from the pencil direction? It's supposed to be in this direction, right? These are supposed to be in this direction, right? Why it is bent away from that particular direction?
Refraction.
So because of the refraction. So refraction produced by this particular material of refractive index mu. Refraction produced by this particular water refractive index of mu. If the refraction is more, bending will be lesser. Sorry, the refractive index is more. The bending refraction will be more or less?
More.
More.
So this is a very usual observation in day-to-day life, but certain cases, some special materials, when you pass light through that materials, or when you see images through that particular material, you are going to see two refracted images. That is the important thing. Instead of one refracted image, you are going to see two refracted images. So something like this. So are you able to see two pencil images here?
Yes, sir.
Same thing, you're going to see two text right here. Able to see, all of you?
Yes,
Yes,
sir.
sir.
So what it means? You are observing two refracted rays or one refracted ray?
Two.
So your light is coming as a two refracted waves. That's why you are seeing two images, one with one refracted wave, another with another refracted wave. Now this is a special property of the crystal. This is a special property of the crystal which splits light into two refracted rays. When the light passes through this particular material, it is going to split into two refracted rays and it's going to produce two images of the particular thing which we want to observe. So this phenomena is called double refraction. Okay, I'll show the video and a demonstration for the better understanding. So before that, let me define the double refraction. So you can see here, when a beam of unpolarized light passes through a certain crystal, especially remember this particular context, you are going to send your unpolarized light through an anisotropic crystal. We'll see what it is and all, but remember this term. So when light passes through an anisotropic crystal, such as calcite or quartz, the refracted lights, once it enters into them, suppose this is an anisotropic crystal here, calcite crystal here, and you are sending an unpolarized light. The moment it enters into the material, it split into two refracted rays, R1 and R2. Okay, split into two refracted rays as shown in the figure. This phenomena, this entire phenomena is called double refraction. You are going to get two refracted rays, R1 and R2. This entire phenomena is called double refraction. This will happen only in anisotropic materials. We'll see why it happen only with the anisotropic materials, not with the other materials. Can you observe here the difference between this and this? Did you observe the difference between those two images?
Yes.
Yes, sir.
This is isotropic crystal and this is anisotropic crystal. We'll see what it is and all in a moment. So if you see here, there are two refracted rays here. There is only one refracted image, I would say. Okay. Now, this is a very important thing to understand why you are getting two refracted images. So, when you have a isotropic crystal, so something like this, if you have simple cubic symmetry, suppose you have a material like glass or water, okay, where all the atoms arrangement is identical from any direction. So, if you see from this direction, or this direction, or this direction, or arrangement of atoms is same or different, environment of the atoms.
Same, sir.
Suppose light pass through this direction or this direction, will light encounter the same environment or different environment?
Same.
Same environment.
Same environment.
So same environment, as a result, you are going to see only one refracted image. One refracted image. Suppose if you consider other crystal where these crystals are called anisotropic crystal, where the arrangement of your atoms are not in a, like if you see from this direction, you will see different kind of atomic arrangement. If you see from this direction, different kind of atomic arrangement, this direction, different kind of atomic arrangement. Okay. Now, when you pass unpolarized light having all the components. So, your vertical component, your horizontal component, for the simple understanding. Okay. When this unpolarized light pass through this kind of crystal, your both horizontal component, vertical component feel the same environment. So they travel with the same velocity or different velocity?
Same.
So same velocity. As a result, you are not going to see two refract images. Whereas, suppose if I send light through this and through this, will they travel same velocity?
No, sir.
No, that's fine. That's first point. So depending on the crystal direction, your velocity of the light wave will change. Suppose if I send from this direction, both horizontal component, vertical component, let us assume. Now tell me which one will move faster, which one will move slower. Along the top axis, if I send the light, something like this. Now tell me which component will move faster, which component will move slow.
Horizontal will move faster.
Okay. So yeah, the horizontal will move, the dot will move faster because they interact less with the atoms. If you look at here, these vertical components will interact with all these atoms. Whereas this horizontal component will move in and out, something like this. It will not interact with any atoms or maybe less number of atoms compared to your vertical component. As a result, you are going to get two waves. Agree all of you now? Yes or no, at least?
Yes, sir.
So
Yes,
you're having two waves propagating in the crystal medium, one with slow velocity, one with higher velocity. As a result, you see one image for the slow moving wave, one with the fast moving wave. Okay. So that means what is the slow moving wave? In this case, vertical component is a slow moving wave, and in this case, horizontal component is a slow moving wave. So that's whatever we discussed here. If you look at here, what are the two waves here? One is vertical, one is horizontal. So it can be other way around. Sometimes vertical will travel faster, horizontal will move slower, or sometimes horizontal will move faster, vertical will move slower, depending upon the crystal material, which type of material, which type of crystal you have chosen for the double refraction phenomena. So these two rays are called extraordinary ray, ordinary ray. Please remember, the one which is having a vertical component, that particular ray is called extraordinary ray, and another one is called ordinary ray. We will see why it is named in such a way that in the exam they will ask you to write what is E ray and O ray sometimes, or in the Viva question. So there was a funny incident happened last semester. So the question was asked to some student. So he said O ray means ordinary ray and E ray means engineering ray. Okay. So make sure remember your E ray is extraordinary ray and O ray is ordinary ray. Okay. Not engineering ray. Okay. So this is what is meant by a double refraction and how you are getting the two refracted waves because of your anisotropy of the crystal. Remember this particular point. Because of the anisotropy in the crystal only, you will get the double refraction phenomena. Otherwise, you don't get it. And remember, even though this anisotropy crystal, at least along one direction, along one direction, if you send the light, your light will have the same identical environment. In that case, you don't see the double refraction. Please remember, even though it is anisotropic crystal, but any crystal along one particular direction, your light pass through the particular direction, it has the identical environment. As a result, along that particular direction, you don't get the double refraction phenomenon. We'll see what is that particular direction and all. So before that, let me show you the original video of double refracting crystal. It will be more easy for you to understand. So you can see here he is going to explain, like show the double refraction calisate crystal. So just skip this introduction part. We'll directly go to the. So what he is holding is a calisate crystal in his hand. It available in that particular shape naturally. You don't have to prepare it in that way. Sometimes you can cut it and all. So please listen carefully now. So he has written some text on the paper and he is going to put a calisate crystal over the text. Okay, and we are going to see two images of text. So please watch. Are you able to see two images? All of you?
Yes,
Yes,
sir.
Yeah. So if you put a normal scale, a normal glass, you don't see two images. That's because of the anisotropic produced by your special crystals. Now watch carefully. It's going to rotate. Now tell me what is your observation. What is your observation?
one image
Sir,
is
at
fixed,
an
one image
angle.
is rotating.
Yeah, one image is fixed, one image is rotating. Now you can see even other direction also you are getting double refraction. Okay, so that's fine. So I hope I'm clear with double refraction now. So we'll proceed further. We'll come back to the video again, not an issue. Okay. So in the exam, they will ask you to explain a double refraction phenomena in a calisate crystal. So you're supposed to draw this figure first, and with a 3D illustration, and you write this extraordinary ray and this is the ordinary ray. Okay. So this is the original calisate crystal, how they look like. So you need to write certain symmetry related details to the related to the calisate. You are supposed to write it's a transparent material and the formula is calcium carbonate calisate crystal, and it's a rhomboidal class of hexagonal system, and you have special corners called blunt corners A and G. Okay, where you can see equal angles with all the three faces. So these are called blunt corners for the particular crystals. So why it is important, we'll see now. So this next topic is optic axis and it's important. Please listen. So if you remember your calisate crystal symmetry, this is your symmetry. Now we are going to define a optic axis. We'll see what it is and all in a moment. So any line passing through any one of the blunt corners, that means here A and G are blunt corners. Okay, any line passing through blunt corners, making equal angles with the three faces. So it's going to make equal angles with the three faces here. Sorry, here, here, and here. So three angles. Okay. With the three faces, which means there is a optic axis. Okay. So that means if you draw any line along the blunt corners, okay, something like this or something like this. Okay. Okay. So that particular line is called optic axis. It's a direction actually. It's not the particular line. It's a direction. Any line parallel to that particular line is called optic axis. So what is the specialty of the optic axis is along this direction. Suppose in case of calisate crystal, if you look along this direction, okay, you will see identical environment for the light. Suppose light is passing through this direction or this direction or this direction, your light going to see the identical environment. When you have an identical environment, what happens to your double refraction? Will it happen or will not happen?
Will not happen.
Will not happen. So that is the specialty of the optic axis. Optic axis is not line, it is actually direction. So you are defining one direction which has to pass through these blunt corners. okay, or anything parallel to the line which is passing through the blunt corners. Okay, now this plane, if you look at this plane, ACGE. ACGE is a one which we are going to cut from the crystal. So this something like look like something like this. So this particular frame, this particular plane, we are going to cut it by a machine, and we are going to take that as a calcite crystal for the double refraction phenomena. Now this is your optic axis. Agree, A to G is your optic axis. This is your optic axis. If you send light through this particular direction, you are not going to get any double refraction, please remember. But if I send from this direction, this direction, this direction, will I get double refraction or not?
Will get.
Yeah, so all the four directions you are going to get the double refraction, because your optic axis is somewhere here. Other places you are not going to have identical environment. You are going to have different environment for horizontal component and vertical component. Okay, and please remember these angles also. These angles, one is 109 degrees, other one is 71 degrees, because these angles will come once again. So this is a specialty of your optic axis and its importance. Okay, now as I said, it is very clearly mentioned. Optic axis is a direction, not a particular line. So any unpolarized light traveling along the optic axis does not split into ordinary and extraordinary, because of it's going to experience the same identical environment. And remember, all the optical properties along the crystal, like along the optic axis, are symmetrical. You are going to get identical properties along that particular direction. Okay. So there are two kind of crystals. One is uniaxial crystal, other one is biaxial crystals. In uniaxial crystal, you are going to get single optic axis. You are going to get single optic axis, whereas in biaxial crystal, you are going to have two optic axis. That means your light going to see two identical environments along two particular directions. So that is what is meant by uniaxial and biaxial crystals. Now coming to the next thing, this is a principal section. So it is straight away whatever we discussed just now. You take any plane which contain the optic axis. So if I take this plane, AC GE plane in the calcite crystal, so you are going to take this plane, and it's going to contain the optic axis. If you remember, if you look at here, there is the optic axis inside this particular plane, and perpendicular to both the opposite faces. It's perpendicular opposite faces. So this is called principal section. This principal section will be cut and used for the production of double refraction phenomena in calcite crystal. You can do it directly, but if you take this way, you're going to get the slice of your calcite crystal. So it is easy to do the experiment, and you know clearly that along this particular axis only you don't get double refraction, and other direction you're going to get the double refraction phenomenon. That's why if you look at all the figures, so this is a calcite crystal. Now where is the optic axis in this? Along this direction. So this is your optic axis direction, and this is your 79 degrees angle, and this is 109 degrees angle, whatever it is, whatever we discussed just now. Okay, fine. Now, to understand this double refraction phenomena, Huygens has given a explanation. So in the exam, they will ask you to write what is double refraction, explain the double refraction based on Huygens explanation. Okay, what he said is like, so the incident light excites two separate wavelets within the crystal. That means when the light strikes at this place, usually in normal crystals, when the light strikes at this place, it's going to generate only one wavefront. That wavefront will propagate with generating of secondary wavelets and so on, and goes like this. Okay, whereas in case of double refracting crystal, it is going to generate two wavefronts. Please remember, it's going to generate two wavefronts. These two wavefronts will travel in the crystal. See, it's going to generate two separate wavelets within the crystal, and these two separate wavelets are called ordinary ray and extraordinary ray, and these two wavelets will travel different velocities inside the crystal. I'll tell you how it will be. Okay, so if you want to understand even more clear fashion, so let's take a a point source in the crystal. Suppose let's say this is your double refracting crystal. Now there is a light source here. When the light produces a first wavelength or first wave, okay, your ordinary ray will travel equal distance in all the directions. Please remember the first point. Your ordinary ray travel same velocity in all directions. As a result, what you are going to see inside this cube, you are going to see what it is, how they look like. If it is travel equal distance in all the directions and your light source is at the center, what kind of wavefront you are going to see?
Circular wavefront.
Circular or spherical?
Spherical.
Spherical wavefront you are going to see. Please remember, you are going to see the spherical wavefront. But when you see in two-dimensional case, how they look like?
Circular.
Yeah, so that is what is meant by a diagram given here. So your ordinary ray look like a circular when you see from the one side, like it's a 2D image of your ordinary wave. Actually, it is actually spherical. It's actually spherical wave inside the double refracting crystal. Suppose this is for ordinary ray, whereas in extraordinary ray, they travel different velocity along different directions. So that means if you take the same crystal once again, listen carefully because this will be foundation for the next topic also. So now if you take the same light point here, suppose let us assume this direction velocity is less, this direction of the velocity is less, and this direction is more. I'm going to get a kind of ellipse. Agree all of you? Yes or no?
Yes, sir.
This side velocity is more. This side, sorry, velocity is less. This side is velocity is more. What is meant by velocity more less? What it means exactly? But it gives you information.
It's an M of a crystal.
No, it's an anisotropic crystal, and along this particular direction, your crystal arrangement is such that it is not going to experience a higher refractive index. Is that fine, all of you? Along this particular direction, your light wave will experience less refractive index. So less refractive index means less dense material, less density. That means the atomic arrangement is less dense this side. Sorry, velocity less means it is more dense this side. Okay, that means your light interact with large number of atoms when it's travel along this direction. Whereas in this direction, where you observe velocity is more, in this direction, your atomic arrangement is such a way that your light wave is not going to interact with large number of atoms. I would say the number of atoms in these directions are less. As a result, the density will be less. When the density will be less, refractive index will be less. When the refractive index is less, and your velocity of the light will be more. So this is how Huygens has explained by considering it generates two wavefronts. One is ordinary, one is extraordinary, and ordinary travel same velocity in all the directions. Extraordinary travel different velocity in different directions. Okay. So they will ask you to, in the exam, they will ask you to write what are the properties of ordinary ray and extraordinary ray. So you are supposed to write both are plane polarized, as you have already seen in the animation all the places. So this is also plane polarized, this is also plane polarized, only one is vertical, one is horizontal. Okay, and if you remember, your ordinary ray obey ordinary laws of reflection, all the reflection, refraction, all those things. Whereas your extraordinary will not obey, does not obey the ordinary laws of, because it travel different velocity in different directions. So that's why it will not obey the ordinary laws of refraction. And this already seen is a horizontally plane polarized, and this vertically plane polarized, and this also we have seen your ordinary travel same velocity in all the direction, your extraordinary travel different velocity in different directions. Especially in case of calisate, this will be asked as a multiple choice question. So please remember, they will ask you in case of calisate crystal, your extraordinary travel faster than ordinary. That means velocity of extraordinary ray greater than velocity of ordinary ray. So in terms, now tell me in terms of refractive index, which one will have a more refractive index, ordinary or extraordinary?
Ordinary.
Yeah, so when a velocity of external is greater means it is having a lesser refractive index. This having less velocity means it having a more refractive. That means you are going to have mu 0 greater than mu. That means your ordinary ray going to experience higher refractive index when it passes through the calicetic crystal, and your extraordinary ray going to experience less refractive index when it passes through the calicetic crystal. Now let us take a simple example of calicetic crystal. Now this is my calicetic crystal. Now my light source is somewhere here. Okay, now based on this equation, tell me whether sphere will be inside the ellipse or ellipse inside the sphere.
Sphere
Ellipse
in
will be
Inside ellipse, sir.
Sphere inside the
Ellipse.
ellipse.
ellipse, because your external is traveling faster, so as a result you are going to get ellipse fast. Ellipse travel faster, and your sphere will travel lesser speed. Okay, so I'll show the original image. It will be more clear for you. Okay, so if you look at here, so are you able to see the figure? All of you able to see the figure?
Yes, sir.
Yes, sir.
So if you look at the example calcium crystal where your external ray is traveling faster and your ordinary traveling is slower, as a result you are going to see ellipse inside the sphere inside the ellipse. So this kind of crystals are called negative crystals because your ordinary ray is traveling lesser than extraordinary. So usually in case of positive crystal, your ordinary ray travel faster than the extraordinary. So in this case, what happens when the ordinary ray travel faster? You are going to get ellipse inside the sphere, right?
Yes, sir.
Okay. So in the exam, they will ask you to draw the figures for positive crystals and negative crystal. You are supposed to draw for a positive crystal. You are supposed to draw ellipse inside the circle or ellipse inside the sphere. In case of negative crystal, you are supposed to draw a sphere inside the ellipse. So based on which refractive index is more or which velocity of the ray is faster or slower. Okay, so this is what is meant by positive crystal, negative crystal. Please try to understand the concept how these waveforms has come. When E ray is ordinary travel faster, so you're going to get sphere first. Since E ray is traveling slower, it's going to be inside the sphere. Whereas in this case, it is other way around. So you're going to get extraordinary faster. So that's why it's traveling more, and ordinary traveling slower. So it's going to get a sphere inside. So this is what is meant by positive crystals and negative crystals. Okay, we'll go back and we'll try to see here. Now how to demonstrate the double refraction. Whether, see, we have said it like both are plane polarized, one is horizontal, one is vertical. Whether we want to confirm it, whether they really vertically polarized or horizontally polarized, how do you do that? Suppose if I want to confirm my ordinary or external plane polarized or not, how do you confirm that?
By analyzer.
Yeah, so what you do is you put one analyzer above this figure. So if you remember this diagram, suppose if I keep one analyzer over this, what happens? Suppose if I keep one analyzer over this, what happens to your images? Both will appear or only will appear?
only one kind of
Both.
image.
Yeah.
Only one.
So if I rotate the analyzer, what happens to image?
A single image will come, sir.
Yeah. So as you rotate it, one image will disappear, another image will come, because you are blocking one kind of polarized light and allowing another polarized light. So when you rotate it, it does other job. It rotates other side. So as a result, other image will appear and the previous image will disappear. That we are going to see in a moment. Let's see how you are going to demonstrate and how you are going to find out which is ordinary, which is extraordinary also. Okay. So let's stop here and let's try to forward it and let's show you. Yeah, now you can see here is going to show you, you're going to demonstrate as far how to check whether they are really polarized or not. So there is a polarizer. sorry, it's not, it's analyzer now in this case. Now it's going to keep this analyzer over this image. We are going to see only one image. Okay, so please observe carefully. Yeah, is this clear, all of you?
Yes, sir.
One image is immediately disappeared. Okay, now it's going to rotate this polar analyzer. You can see now one image will disappear, other will come into picture. Are you able to see?
Yes, sir.
Yeah.
Yes, sir.
So that means both are plane polarized. Agree? Okay, this is how we can identify both are plane polarized or not. Okay. So this is all about how to identify this thing. Now we'll try to demonstrate how to identify which is ordinary and which is extraordinary. Okay. And we'll see. The same thing, double refracting crystal here. You can see two lines of images. Same thing. Same thing you can see here is also demonstrating same fashion. Now you can see two lines. The moment you keep the analyzer, you're going to see only one line. As you rotate, one line will disappear, other will come into picture. Yeah, now you are going to see the original video. See, he is actually passing a laser light through a calcite crystal. How many are able to see now? If you look at here, how many are able to see? How many? Three. Why three? We said only two, right? Why three here?
I think it is from three faces.
Oh, okay, fine. So actually it is not three. Actually it is a reflection of the laser light. Okay. Two refract image. One is a reflection of the laser light. We'll see how when you rotate that other side, you'll see the only two images. Okay. We'll see that in a moment. It's going to hold it and you're going to rotate it for us to show. Okay. Just a second. I'll show you. Yeah. Now both are overlapped on each other. We could not see two images, but you can see slightly. Are you able to see two images? Now again reflection has come. We'll proceed further. It will be more clear in a moment. Yeah, now you can see. How many are able to see now?
Yes,
Yeah.
sir.
Now it is only two because we are seeing other side, the transmitted side of your calcite crystal. You see two refracted images. One is ordinary, one is extraordinary image. Okay. The same thing, you can do all kind of display and that's fine. Anyway, we are going to see now how to identify which is ordinary and which is extraordinary. So this is the last part in double refraction. So sometimes it is called birefringence also, double refraction phenomena. So what he did is he kept one ink dot or ink mark on a paper, some small dot, and he kept a calcite crystal over it. The moment you keep the calcite crystal, you are going to see two dots. So hope you can see two dots, I guess. Okay. Now when he rotates your calcite crystal, one image going to be rotated, one image going to be fixed. You can observe carefully. So again, he's testing the polarizer. So same thing happening. So same thing, one is appearing, one is disappearing. This is one way of confirming both refracted rays as plane polarized or not. Now there is another way. Now you can check. Yeah, now you can check here. So if you observe carefully here, one image is fixed, one image is rotating, right? Say sir, at least. One image,
Yes, sir.
yeah, one image is fixed, one image is rotating. Please remember, the image which is fixed is called ordinary image, or the image related to the ordinary ray. The one which is rotating, as we rotate the crystal, so that is called extraordinary ray, or the image related to the extraordinary ray. Why? Because your ordinary ray will travel same direction, sorry, same velocity in all the direction. As a result, your image will not be distorted, your image will be stable. Whereas in case of extraordinary ray, it has a directional dependent property. As you rotate it, it's change its velocity, change the refractive index. As a result, you are going to see the movement of the image, because your refraction is keep on changing for the extraordinary. So that's how you can find out which image related to the ordinary ray and which image related to the extraordinary ray. Is this clear, all of you? Double refraction.
Yes, sir.
Yes, sir.
So in the exam, it will be asked for the long answer question. You are supposed to define what is meant by double refraction, and what is the calisate crystal, and what is the optic axis, what is the principal section. Then you have to describe what are the properties of ordinary ray and extraordinary ray. Then you have to tell them how to identify ordinary ray and extraordinary ray, and how to confirm whether ordinary and extraordinary are plane polarized or not by using an analyzer. So these are the things you are supposed to write when it comes in the exam for the long answer question. Okay, so this all of double refraction, and we have discussed what is meant by positive crystal and negative crystal, also based on velocity of your ordinary and extraordinary. So I'm sure, please make sure, remember, this will be definitely asked in the exam, sorry, in the quiz exams, maybe in the lab or maybe in the viva. Please make it a star mark. Definitely you will get confused between positive crystal and negative crystal. So make sure, remember properly, and try to remember how these diagrams are getting formed. Okay. Now coming to the next case, water wave plate and off wave plate. So please listen carefully. So we are going to use the same phenomena of double refraction to construct a quarter wave plate and half wave plate. We see why it is called quarter wave plate and half wave plate. So before that, what I'm going to do is I'm going to take a calisate crystal. Listen carefully. I'm taking my calisate crystal, something like this, and I'm taking my optic axis at the top surface. This is my optic. Along this direction is my optic axis. So this is my optic axis. Please listen. Now if I pass my unfold light through this particular crystal, listen carefully. So I've taken my calisate crystal. I cut such a way that I'm getting my optic axis along this direction. So all these things are optic axis. All these things are optic axis. All these planes are optic axis planes. Okay. Now tell me what happens inside the calisate crystal now. I'm sending my ordinary light of some thickness T. Now what happens inside the crystal? Tell me. What happens to ordinary light? Will they split or not?
Splits.
Okay, they will split into two refracted rays. Okay, let's say this one is ordinary, one is extraordinary. Now tell me, will they travel same distance or different distance in a given time?
Different.
So suppose, let's say, for a fixed time, so let's say the ordinary travel this much distance and extraordinary travel only this much distance. Okay, will they have phase difference and path difference?
Yes, sir.
So when a unpolarized light pass through your calisate crystal, which is called normal incident, this is called normal incidence case. Please remember, this is called normal incidence case because your optic axis is perpendicular to your direction of your incident. So that's why I call it a normal incidence case. So in this case, you are going to get two rays out of that, but these two rays will have a path difference as well as phase difference. Suppose your thickness is such a way that if it is going to produce a path difference of lambda by 4, we call that particular plate as a quarter wave plate. Is that fine, all of you? Is this clear, all of you?
Yes, sir.
You're going to choose a thickness such a way that when unpolarized light pass through your calcium crystal, if it is going to produce a path difference of lambda by 4 between ordinary ray and extraordinary ray, we call that particular plate of thickness as a quarter wave plate, because it is introducing a lambda by 4 path difference. Or in terms of phase difference, how much? In terms of phase difference,
Pi by 2.
Pi by 2.
Pi by
Pi
2.
by 2. So very clear. Okay. So when you pass ordinary light through a calcium crystal of appropriate thickness T, it is going to produce a lambda by 4 path difference and pi by 2 phase difference. Okay. Now tell me, if I add these two waves, what I'm going to get? What I'm going to get if I add those two waves? I showed in
Minimum.
the yesterday class also how to produce a circularly polarized light. Remember or not? Your extraordinary ray is one polarization, and ordinary ray having one polarization, having a phase difference of pi by 2. So let me play you once again just for
Circular
you.
fringes will come, sir.
Yeah. So when you look at, suppose let's take again. So let's make it one. Is it fine now? Now we are having two plane waves. One is horizontal, one is vertical, and they are having a phase difference of pi by 2. As a result, you are going to get a circularly polarized light. So that means whenever you pass light through a quarter wave plate, you can expect output as two waves which are having a path difference of lambda by 4, phase difference of pi by 2. If you add those two, you are going to get the circularly polarized light. Suppose if you want to produce lambda by 2 thickness or lambda by 2 path difference, what I'm supposed to do? For quarter wave plate, it is producing a lambda by 4 path difference. Suppose if I want to make it lambda by path difference, what I'm supposed to make for my crystal? Should I increase thickness or should I decrease thickness?
Increase.
Say, should I increase my thickness or decrease my thickness?
Increase.
Yeah, as you increase it, your E ray undergoing more effect, and as a result, you are going to increase the path difference between extraordinary and extraordinary. So that means you are going to take a slightly larger thickness crystal. Same thing, you are going to have optic axis here, and you are going to pass your unpolarized light from here, and it's split into two rays. But only thing, this time it is traveling larger distance. I mean, like it is traveling longer distance. As a result, it is going to produce a path difference of lambda by 2, and corresponding phase difference how much? How much will be the phase difference? 5. So it is going to produce a path difference of 5. Okay. So this thickness of the plate, we call it as a half wave plate. So if you want to get a formula, so if you want to measure the path difference between ordinary and extraordinary ray, let's say if you want to measure path difference between ordinary and extraordinary ray, you can write mu0 times T minus or difference. You can take difference, and mu0 times or mu e times T will be equivalent to lambda by 4. So thickness will be lambda by 4 times mu0 minus mu e. Is that fine, all of you? For quarter wave plate. Yes or no? This is a path traveled by your ordinary ray, and this is a path traveled by extraordinary ray. When I take the difference, as I said, quarter wave plate is going to produce a lambda by 4 distance. So if I rewrite, your thickness will be lambda by 4 into mu0 minus mu e. Is this fine, all of you?
Yes, sir.
So that means, so based on the refractive indexes and based on the wavelength, you have to determine the thickness of the crystal. So in the exam, they will ask you to find out what thickness should be there to produce or to act the particular crystal as a quarter wave plate or half wave plate. So they will give you refract indices of mu0 and mu e. Please remember, in case of quarter wave plate, half plate, both the cases, you always take difference. Don't take the subtraction, because if you go back here, what happens in this case? If I take mu0 minus mu e,
Negative.
here it is negative, here it is, sorry, here it is positive, I guess, because your ordinary is traveling faster, means your refract index is less. Yeah, it is negative. Sorry. This is negative, and what about this?
Positive.
Positive. So
Positive.
so you're getting a positive value and negative value, but whereas when you want to measure thickness can be negative. Can thickness be negative?
No, sir.
No. So that's why you should always take difference of these two numbers. You don't consider the positive sign or negative sign. Just take the difference of those two refractive indices, which will be provided in the problem itself, and you find out the which thickness is sufficient to act as a quarter wave plate, or which thickness is sufficient to act as a half wave plate. Okay. So the same thing here, it is discussed the same way. It's a quarter wave plate. This is the formula for quarter wave plate. So wherever I take the minus, it considers a difference of those two numbers, nothing else. Same thing, you are sending unpolarized light, optic axis and thickness T, and path difference is lambda by 4. Corresponding phase difference is 90 degrees. This for quarter wave plate, and this for the half wave plate. If you observe carefully, here thickness is small, the thickness is large, because it's going to produce a path difference of lambda by 2. Now we'll see the last topic for today's lecture, and I'll stop maybe after 10 minutes. Okay. So next one is a Nicols prism. So this is the original Nicols prisms. Okay. So if you remember your double refraction phenomenon in calcium crystal, let me just rewrite once again. You're sending unpolarized light, and you're getting a two rays. One is ordinary, one is extraordinary. Can I use these two for practical application? Can I use output of the calicate crystal for the practical application or not? Tell me. Say yes or no at least. Can I use output of my calicate crystal, which are plain polarized light? Can I use practical application for measuring something or for constructing something? Is it possible?
Yes, sir.
By stopping one of the two rays, we can
Yeah,
use.
very good. So we cannot use it as it is because we are having two. But when you want to make any application, we need only one. If you want to make any application, especially any particular device based on polarization, you need only one kind of polarization. Either you want only vertical or we want only horizontal thing. So in order to do that, we are going to modify my calicate crystal. I'm going to modify my calicate crystal such a way that I'm going to block one of the ray and allow only one particular wave. So that way I'm going to produce only a polarized light in one particular direction. So that is what is meant by Nicols prism. Nicols prism is nothing but modified version of calicate crystal. If you observe carefully, can you observe any difference here? Any observation here? It is a single crystal or two crystals? At least tell me.
Two crystals.
Yeah.
Two crystals.
So this is one calicate crystal. This is another calicate crystal of same calicate. These two are actually part of the same calicate crystal. We cut those two calicate crystals, so one particular direction, one particular angles, and we added with some kind of a material. Okay. And this calicate crystal, if you pass your unpolarized light through this particular input, and you are going to get output somewhere here, it will be only one light. That means only one polarized light. Okay, we'll see how we are going to cut the calicate crystal, how we are going to add with a particular material of particular refractive index, how this refractive index of the material going to play a major role. So please remember, this particular refractive index material going to play a major role in doing or getting one ray is blacked, one ray is allowed. Okay. So just now we have seen, if we want to black one of the ray, so we are going to do that. So it is actually possible. We can do that by doing some modification. So this, as I said, you're going to modify your calcium crystal to a modified version. That modified version is called Nicols prism. So in Nicols prism, so please listen carefully. It works on the principle of total internal reflection. Please remember this particular point. A Nicols prism going to work on the principle of total internal reflection. How it is going to work, we are going to see now. So please listen. This is one calcium crystal of refract index, some refract index, and this is a one refract index. And this is another material called Canada balsam, okay, whose refract index is defined such a way that your refract index of Canada balsam is defined such a way that it undergo total internal reflection, one of the ray, and other ray will be traveled as it is. If you look at the animation here, it will be more clear. Are you able to see animation here?
Yes, sir.
Your light is split into two refracted ways, but one refracted ray is totally inter-reflected by your extra Canada balsam material. Your Canada balsam material is doing a role in producing the total internal reflection for only one particular ray, not for the another particular ray, because the refract index of ordinary and extraordinary is different or same?
Different.
Oh, different. So that means we can selectively achieve total inter-reflection either for ordinary or extraordinary by defining your Canada balsam refract index. So if you define your Canada balsam refract index such a way that you can either you can make total internal reflect either ordinary ray or extraordinary. In this case, your ordinary ray is undergoing total internal reflection and extraordinary ray is not going total internal reflection. We'll see how it is going to be done. But before that, let me show you how to construct the calcium crystal. So first thing, you take the calcium crystal as usual with the, I think these angles are displaced from the original places. Okay. So you're going to have 71 degrees and 109 degrees actually, what we have seen in the calcium crystal case. You're going to grind or you're going to remove a certain material to a certain portion to make this 71 degrees to 68 degrees, to make this 109 to 112 degrees. Okay, you're going to remove the portions or you're going to grind it such a way that these angles become 68 and 112 degrees. This is the first thing you're supposed to take. Okay, once you're done, you're going to cut along the diagonal, along this particular direction you're going to cut. And now you're going to add these two pieces by using a Canada balsam material. If you look at here, this is a Canada balsam material. Okay, this is actually transparent material. Please listen, your Canada balsam is a glue material of transparent material. And here is the important point. Please remember now, this is a very, very important thing to remember. In case of calcite crystal, the refract index of ordinary is 1.65, extraordinary is 1.4. Now tell me velocity of ordinary ray and extraordinary ray, which one is greater, which one is higher?
Extraordinary ray is greater.
higher.
Velocity of extraordinary will travel greater than velocity of ordinary. Okay. Now I'm going to take a adding material or the material which added the two pieces of refract index 1.5. That means this is 1.55. Now your refract index is 1.6 and your refract index is 1.4. Now if you remember the total internal reflection phenomena, suppose let's say this is a water surface. So your light is passing through this medium. Okay, this is the refract index of, let's say water will be 1.5, the air will be 1. Now it will be definitely reflected back at certain angle when the theta is greater than theta c. Or else I'll show the slide here. So this you must be knowing, right? Total internal reflection.
Yes.
When light is passing from higher refracting index medium to a denser medium to rarer medium. Okay. When you keep on changing your angle at one particular angle, that can like critical angle. If your angle of incidence greater than critical angle, your light will be internally reflected back into the same medium. Okay. The same concept we are going to use for our Nicols prism also. Now, if you look at here, if I pass my ordinary light through this particular thing and split into two refractor rays, let's say this is ordinary and this is extraordinary. Okay, now tell me which ray will undergo total internal reflection, which ray has a possibility?
Ordinary ray.
Because your ordinary ray, because your ordinary ray is traveling from higher refract index to lower refract, because your ordinary ray is refract index is 1.6 in this medium. So as a result, your ordinary ray has a possibility to undergo total internal reflection, provided you have to incident your ordinary ray such a way that it's going to make an angle here. That angle should be greater than theta. Say when this happens, this ordinary ray will reflect back into the same medium. But whereas in extraordinary, what happens? Extraordinary, will it undergo total internal reflection?
No, sir.
No, because it is traveling from a rarer medium to denser medium. It just undergo small refraction. Just will come out as a output. Okay. So that means in this way you are actually blocking one of the polarized light or one of the ray by total internal reflection phenomena, and you are able to produce only one polarized light. Is this clear, all of you?
Yes, sir.
Yeah. So that's the same thing we shown in the animation here. Your ordinary ray is undergoing total internal reflection here, and your extraordinary ray just refracted and went out of the particular crystal. So the same thing is shown here in the animation. Okay. So in the exam, they will ask you to construct, like write the principal construction details of Nicols prism. You are supposed to write what is how to construct the Nicols prism, like cutting and grinding and adding those two pieces by Kendall balsam with the refracting index, so and so. And working you have to write, it is based on the total internal reflection phenomena, and you are supposed to write your ordinary ray is traveling from denser medium to rarer medium. So it has a possibility to undergo total internal reflection, provided you have to make the angle at that interface more than critical angle, and your extraordinary traveling from rarer medium to denser medium. As a result, it will not undergo any total internal reflection. It will just come out as it is, as expected, as a single polarized light. So this is what you are supposed to write in the exam. And there is a last point. This is an important point. Okay, this we have discussed. Now this application, how you are going to use Nicols prism as a polarizer as well as analyzer. So this is straight away, this we are using as a polarizer directly. When you pass unpolarized light through a Nicols prism, you are going to eliminate ordinary ray by total internal reflection, and you are getting a polarized light at the output side. If you want to analyze, you are going to take one more Nicols prism. This is one Nicols prism, Nicols 1 and Nicols 2. Now tell me what is the output here? What is the output of the analyzer? Zero,
Extraordinary.
zero or maximum?
Maximum.
Maximum. If I rotate this one,
0.
it will reduce to 0. It will gradually reduce to 0. So that means we can use your Nicols prism as both polarizer as well as analyzer. Agree, all of you?
Yes, sir.
We can use it for producing the polarized light. At the same time, we can use another Nicols prism which can be used to analyze whether the given light is polarized or not by rotating the second analyzer. So this is the application of your Nicols prism as a polarizer as well as analyzer. Okay, I'll show the last video and I'll stop for today. The last video for today's class. Yeah, you can see here. So this is the same thing. There are two Nicols prisms. Yeah, now light will enter into one of the Nicols prism. So please remember, this polarizer and analyzer are the very subjective terms. If it is used for production, we call it the polarizer. If it is used for analyzing, we call it the analyzer. Ideally, both are same. Now you can check. Yeah, now you can clearly see there are two pieces which are joined by Kanda balsam material. Now you are sending the unpolarized light here. Now you can see one light is reflecting. There is ordinary light is totally internally reflected and external is traveling. It will travel because both are parallel to each other. There is no angle between these two polarizer and analyzer. You're going to see the maximum intensity. If you rotate this one, it is going to black the output of the second Nicols prism. Now you can see it is rotated by certain angle. First one will produce as usual. So what happened to second one? Is it allowing or it is blocking?
Blacking, sir.
So see, blacking means what it is exactly, tell me.
Intensity 0.
So blacking means it actually absorbs all the radiation, nothing else. Please remember, as I said, this thing, production of polarized light by selective absorption. So in that case, I said clearly, when you pass light through unpolarized through a particular materials, Rakel salt or tourmaline, it is absorbs all the directions, allow only one particular direction. The same thing happen here. When you rotate your second Nicol to a particular direction, it will not allow, means it will actually absorb that particular radiation, nothing else. Okay. So as a result, you are going to see only zero output at the second Nicol prism side. So that's how you can use your Nicol prism for production of polarized light as well as analyzing the polarized light. Okay. So anything else? I'll stop for today. We'll discuss. There is one more topic left, probably. So this is our last topic left. Probably we can discuss in the next class, I guess. I'm sorry. Yeah. So there is one topic left. One is offset polarity meter is left, that we will discuss in the next class. Any doubts at this point of time? So these two questions are very important for the end exam as well as mid exam. This double refraction phenomena as well as Nicol prism concept, both are very, very important for the end and mid exam purpose. So any other queries at this point of time? Otherwise, I will close for today.
Thank you, sir.
Yeah, fine. So if there are no queries, then fine, we'll close.
Thank you, sir.
Yeah,
Thank you, sir.
Thank you all. There is no lab session today, so
Thank you, sir.
have a nice weekend.
So super.
Thank you, sir.
Thank you, sir.